So welcome to chapter 5. In this chapter, we will discuss synchronization and scheduling. This is a very important chapter insofar as managing computational resources is concerned. So we will look at various aspects such as parallel programs, locking, synchronization, and how we schedule both for regular systems as well as real-time systems. So we'll use the Indian English schedule as opposed to schedule. So it has 4 parts like all chapters. So we'll start with the basics of synchronization, which one needs to know before you know how to actually schedule your tasks. So synchronization has 2 parts. One is user space, one is kernel space, and they are not the same, they are different. Then scheduling also has 2 parts, regular kernel scheduling. And if it's a real-time process, real-time means something associated with a missile or right space, so which has like absolute hard deadlines, then it's a you have a separate set of algorithms. So we will discuss these 4. So you consider a multi-core CPU. So a multi-core CPU would have 2 cores. So Linux calls them different CPUs. So let's also use the same terminology. Let us say they are running exactly the same program, 2 different threads. Count is a global variable, single shared address. Both are trying to increment count. So they will do count plus plus. So count plus plus in assembly will translate to actually 3 instructions. The first is you read count, put it in a register. The second is you increment the register. The third is that from the register you go to the global variable, you update its value. So you can think of this that each line of C code here corresponds to a single line of assembly. So given the fact that we have 3 instructions, running this concurrently is not a good idea, as we shall just see. So what happens is that if they run concurrently, the assumption we are making is that even if you assume that first this executes, then this, well, because there is a dependence chain that will happen, the delay between any 2 consecutive instructions can be indefinitely large, can be very large, right? Is not something that you can predict, because maybe in between this a context switch comes, right? Then a long time later the next instruction, and again a context switch comes, right? Some sort of an event of interest happens. So because of this, you could have an interleaving that looks like this, which is that both the threads read the value of count almost at the same time. They increment count, the register that is storing the value, almost at the same time. So if the starting value is 0, then both of them will set this to 1. And finally, both of them will write the incremented value to the global variable count almost at the same time. So the final value will actually be 1, but there are 2 increments, it should have been 2. This is because there is no synchronization between the threads. Hence, we have such kind of an overlap, which is not a desirable overlap. Given the fact that there were 2 increments, the final value should have been 2. But as we see, the final value is 1, which for us is not a desirable outcome. So concurrently incrementing the count variable is hard, is difficult. What is the main issue? That the instruction sequences, if you think of these as 3 instructions, they are overlapping like that. All right. So they are overlapping. And if they would be separate, then there would have been no issue. This way, that way. So that is why we need synchronization, such that this sequence of 3 instructions, known as the critical section, only one thread can execute instructions in a critical section at any point of time. So this basically means that thread number 1 comes, or thread 2 comes, one of them, you acquire what is called a lock. So lock is a permission to execute the critical section, and only one such permission can be given at any point of time. So you acquire the lock, then you execute these 3 instructions. and then you release the lock. So how you acquire and release is we'll discuss later. But this is synchronization, where the critical section known as the CS is protected with a lock. Once you exit the CS, you unlock it. Then some other thread can acquire the lock and again execute the CS and again unlock it. So this is how it happens. So in a certain sense, even though they are parallel threads, insofar as the critical section is concerned, they become sequential. One runs, then another, then another. Then they parallelize immediately after leaving this. So this ensures that you have correctness. So the kind of situation we saw in the last slide will not happen. All right. So how is a lock implemented? Well, the way that a lock is implemented for sequentializing things, as you can see here, where thread 1 finishes its job and thread 2 does. So all that a lock is that it is one global address. So of course, you can have like 100 locks. Every lock will have its own address. So the lock will basically point to an address. So the convention that we can have is that if the address stores 0, the lock is free. If the address stores 1, the lock is occupied. All right. So the thing is that an unlocked state, so when you lock it, you try to convert from 0 to 1. If you are successful in converting, then you acquire the lock. And nobody else can acquire until the thread that has acquired the lock converts 1 to 0. So it is as simple as that. Of course, if a thread that holds the lock that gets context switched, then everybody else ends up waiting. So this is kind of a negative consequence of having locks. So that is why implementing locks is actually, it's an area of study in itself. So a lot of papers have been written, books have been written on how to implement locks efficiently, especially if there are a lot of processes. So what happens is that we lock the memory address A. So the first thing is that we keep testing if the memory address has a 0 or not. Right? So this is known as a test operation, where you keep testing whether it has a 0 or not. 0 means it's free. So if let's say there are multiple threads and there is a single lock address with value 1, all of them will test if the value is 0 or not. Once they perceive it to be 0, they try to atomically. Atomically is an interesting word, so we will keep encountering this. So atomically, the meaning means instantaneously. It is something where nobody sees an intermediate state. So either it has not started or it has finished. So the operation is never seen in the middle. So it appears to execute instantaneously, even though it may not execute instantaneously, but it appears to execute instantaneously. So what every thread will like to do is atomically set the value in the lock address to 1, which means convert 0 to 1. Only one of the threads will be successful. So when you try to atomically set it, the return value is whether you were successful in atomically setting it or not. If you were successful, then the return value will be 1. Otherwise, the return value will be 0, which means you are not successful. So if you are not successful, you will again go back to this point and keep trying again. In case you are successful, then you can go ahead and access the critical sections. It's more like a trust-based system, where basically threads can lie, but of course you wrote them, so there's no reason for them to lie. And then the key operation is trying to set a 0 to a 1 and finding out if you are successful in this process or not. So this is where actually you need hardware support. So we'll discuss this in a second. But this is the broad idea of a locking mechanism, where you are basically doing a test to see whether I should even try to set it or not. And then if you see that the value is 0, you are trying to do a test and set. Test and set basically means see if it is 0, immediately make it 1, all in one go. So this is a test and set. So this lock is known as a test and set or a TTAS lock, right? Why TTAS? Because first you are testing. You will not even attempt to change its value if you think there is no point. The moment you see a 0, it makes sense to try to change. So trying to change means what? Test and set, which means test that it is 0 and convert 0 to 1. If you are successful, you are notified, or you are notified otherwise. So test and set lock is the most basic kind of lock. Is obviously not very efficient. The reason it is not very efficient is that all the threads are looping to check, is it 0, is it 0, is it 0. And the moment you see it to be 0, all of them kind of go at the same time. And that basically writing, essentially in any, you're trying to write 0 to 1 is a write operation. A write operation is very expensive in modern hardware, right? In a multi-core CPU, a write operation is very expensive. And so basically because the cache line has to bounce between CPUs, and that is not an efficient thing, which is why this lock is not efficient, and clearly Linux does not, it uses variants of this, but the more efficient locks are not this. So we'll discuss. Linux has a lot of locks.
Let us now look at the process of unlocking. So the process of unlocking is actually quite simple. All that we do is we set the contents of the lock location to 0. That is all that has to be done. Subsequently, there are many contending threads, as we can see over here. They will keep on testing if the address is equal to 0. The moment they find it, they will try to atomically set it to 1. Whoever is successful will acquire the lock, and the rest will go back and try. So when we discuss more about memory models and memory consistency, we will see that there is a need to add something called a memory barrier here. So this is not as simple as setting the value of a location to 0. There is something additional involved over here, which includes what is called adding a barrier. But it is better discussed in the next lecture, not in this one. So the sum total is that before entering a critical section, we acquire a lock. This can take a long time depending upon the amount of contention. Once the critical section is over, there is a need to release the lock using this unlock mechanism.
So there is a fair amount of theory here. So a lot of this is covered in my book on advanced architecture. But we will discuss a small part of it, whatever is relevant from an OS point of view. So we need to understand that why doesn't this code that had count plus plus without locks, what was the main issue, right? Theoretically, what was happening? We do all understand intuitively what was happening, but from a theoretical standpoint, what was happening? So we have something called a data race. A data race means there is one data, multiple threads are racing to update it. If all the threads are reading, there can be no data race. There has to be at least one writer. So there has to be a conflicting access, which means one of them needs to write. When one of them is writing, that's when you can have these funny situations that we just looked at. If you want to look at it formally, then we need to define something called a happens before relationship. So what is a happens before relationship? So consider this write to the count. So after this write, we have an unlock. All right. So this means the write needs to happen first. Then you need to unlock, because once you have unlocked, the entire world needs to see that you have written. All right. So there is clearly a happens before relationship between the write and the unlock. All right. Then when you lock, clearly you need to unlock first before locking. So there is a happens before relationship between the unlock and the lock. And then when you read the value of count, you need to lock first and then read. So again, there is a happens before relationship between the first read and the lock acquire. So now if you see, there is a path of happens before relationships from this write over here to this read over here, where all the edges are happens before edges, all of them. So happens before relationship is a transitive relationship, which means that if event A happened before event B happened before event C, then A happened before event C. All right. So in this case, we can clearly infer that there is a happens before relationship between the write over here and the read over here, because there is a path, right, that follows the transitivity property from the write to the read. So we can say that there is a happens before relationship between them. So the way that we will define data races is essentially in terms of these happens before relationships. So two accesses across two different threads are said to constitute a data race if they are conflicting and concurrent accesses. Right? So data race does not happen for accesses in the same thread. Across threads, you have a data race if they obviously access the same address and they are conflicting and concurrent. So conflicting means one of them is at least a write. Concurrent is something that we need to define. So this basically means that both the accesses are roughly happening at the same point of time. So as we said, both these count accesses, if let's say this happens and then 10 years later this count access happens, then they are not happening at the same point of time. But in this case, what does same point of time mean formally? This means that there is no happens before relationship between, let's say, accesses to count in one thread and accesses to count in the other thread. So the important thing you need to remember, in distributed or concurrent systems theory, absolute times are never used. So you never say that something happened at this point and that. Well, there can be, we'll nuance this argument later, but in general, in the theory, absolute times are not used. There are exceptions, which we will discuss, but if you look at the generality of the theory, then absolute times don't matter. What matters are only relative times or causal times. That I did something, you took my return value. That means I must have executed before you did. Otherwise, how did you get the return value? So if you look at it that way, if let's say there is no happens before path between any two events, and events are memory events, memory read and write, right? Global memory read and write. If there is no path, they are concurrent, regardless of their actual time at which they executed. This is the definition. That if there is a path, they cannot be concurrent, right? But if there is no path between them, then they are deemed to be concurrent. And this constitutes a data race, which means that data race, as I said, two separate threads, same address, conflicting and concurrent. Right? So that is the definition of a data race. So the reason that your count plus plus does not work correctly is basically because there is a data race. All right. So to remove data races, what do you do? I want to remove data races because clearly having data races is not doing me any good. So I'll have two different updates to count and then the final answer should be 2. I am getting 1. That is clearly non-intuitive. It's not correct. So I want to create a properly labeled program called a PL program. So the program will be written in such a way that regardless of whichever hardware you run it on, you'll never have a data race. Because you think about this, so think about the practicality of this definition. Let us say you are writing some code. It may be running on an Intel processor today. Maybe you want to run it on a Mac, which is an ARM processor. Maybe later on you want to run it on RISC-V. It should not be the case that there is no data race on Intel, but there is a data race on RISC-V. It basically means automatically that your program is incorrect. So for every new hardware, you are not going to recode your program, right? That is a lot of additional effort. So you want to write something, leave it out in the market and expect that it is going to run everywhere and the execution will be devoid of data races. So there is some theory, there is a lot of theory which is covered in a typical advanced architecture course. But if I were to just summarize it for you, A properly labeled program is one program where all the shared variables, like we are not concerned about private variables here. A shared variable is something shared across threads that is always accessed in the context of a critical section. It is always protected, which means that if two different threads are accessing the same shared variable and one of them is a write, then the lock protection has to be there. Lock protection being there means that it is being executed in a critical section. So kindly look at this program. This program is not properly labeled, hence, so it is not that if the program is not properly labeled, it will have a data race. Not necessarily, because the point is the execution can be such that you can have count plus plus first and then one more. So even though yes, there is a data race in the sense there is no happens before relationship, the execution is not incorrect. The outcome will be 2. What a data race says is that there is a possibility for the execution being incorrect. Whether it actually is or not, well, that depends on the execution itself. But if you do not have data races, then these kind of errors will not happen. So the main aim is to eliminate it. And to eliminate it, if I write my programs in a properly labeled fashion, there is a proof that data races will not be there. If data races are not there, then there are further proofs of what can be guaranteed. But the kind of behavior you saw, that will not happen. So in this case, for accessing locations A, B, and C, I am locking the variable X. And for accessing the variables D, E, and C, I am locking the variable Y for 2 different threads. So these are the choices that thread 1 is making. These are the choices that thread 2 is making. My claim is that this program is data race prone, and that is something that you need to prove. So the answer in the class was correctly given, that consider location C. If thread 1 locks X to access C and thread 2 locks Y to access C, this is not allowed. This basically means that C is not being accessed within a critical section. That is because if thread 1 has accessed C, thread 2 can get in because it is acquiring a different lock, and that is not allowed. So thread 2 can access X and Y, right? It can acquire X and Y, but there has to be something in common. If there is nothing in common, your properly labeled constraint will not hold. And given that it does not hold, data races can happen, right? Probability. I mean, I need to rephrase that. Data races will always be there because there is no happens before relationship. But errors due to data races can happen. So when I'm saying data races will be there, but not all data races are actually erroneous. They don't lead to errors. They lead to errors only when you see something that is obviously non-intuitive, right? So data race in itself is probabilistically error prone, right? And the point is that you want to eliminate them at the source, such that if there are no data races, there are no data race induced errors. For that, you properly label, and this example is not an example of proper labeling. There are other issues with locks. So locks, of course, solve some problems, but introduce few more problems of their own, right? So it is not that they are completely trouble-free or problem-free. They introduce other problems of their own. So assume that thread 1 locks X and then tries to lock Y. And thread 2 locks Y and then tries to lock X. Then we clearly have a deadlock situation here, because once you have X, you don't have Y. All right, where will you get Y from? You need from 2, but 2 is waiting on X. So as you can see, there is a clear circular waiting pattern over here, where X is waiting on Y, Y is waiting on X, and nobody is able to make progress. So this is the problem with locks. Locks can lead to deadlocks. And if you have a deadlock, no one makes any progress, then what do you do? Other than terminating or doing some other coercive action, you really can't do much. So there are 4 conditions for deadlocks. So let us evaluate these 4 conditions in the context of this example. The first is hold and wait. Hold and wait means I'm holding one lock and I'm trying to wait on a one lock. Right? So that is hold and wait. Hold and wait is required. So that is my waiting condition. The second is no preemption in the sense that a lock is not being taken away from you, right? So preemption means something being taken away. Like the CPU being taken away, that's CPU preemption. So lock is not being forcefully removed, it's not being forcefully taken away. So if it is not being taken away, you have a situation of no preemption that prevails. Then we have mutual exclusion, which basically means that a lock at any one point of time can be held by only one thread. Two threads can't hold it. That follows by definition. That is obvious, right? That only one thread can hold on to it at one point of time. The fourth thing is circular wait, that X. So you can have more threads involved. X is waiting on Y, Y on Z, Z on X, right? So essentially threads are waiting, but also you can say that, I've acquired lock X, I'm waiting on Y. So I can add an arrow from X to Y. Then I've acquired Y, I'm waiting on X. See, we have a circular wait. So all four conditions are needed for a deadlock, right? So all four conditions are needed. So that doesn't mean that if all four are there, you'll have a deadlock 100% of the time. No, that you will not. But the point is that if you don't have all four of the conditions holding, you'll never have a deadlock, right? So you have to interpret this correctly. So it's like saying that all crows are birds, but clearly all birds are not crows. All right. So it's a classic, subset kind of logic. So in this case, there are four conditions for a deadlock, and all four need to hold for a deadlock to happen. But it's not the case that if all four are holding, a deadlock will happen for sure, right? So, but in any system that you design should be able to do something with these four. So what you do is for hold and wait, in case there is a deadlock, all right? So then what you do is that if you are waiting for too long, then you just simply release its resources. You don't allow it to hold and wait. So let's say you kill one of the threads, at least let there be one casualty in the bigger and larger interests of the system. No preemption, same thing, that forcefully take away the resources. So hold and wait also is that, instead of you release, next time you say that you acquire either all of them together or you don't acquire. So hold and wait, that is what it means. Otherwise, you may confuse between these two. So hold and wait, if you really want to avoid, the right thing would be either you acquire all the resources or you acquire nothing. But don't acquire a subset and wait for the other partial subset. No preemption means forcefully take away. I agree, it's a bad idea for that process. But for the rest, mutual exclusion, this is integral to the definition of a lock, that mutual exclusion has to be provided. This basically means that if I'm holding on to a lock, nobody else can hold on to it. Circular wait is the one that we will focus the most in our deadlock avoidance algorithms, where we will see that you just break circular, design a protocol in such a way that circular waits will not happen. Right? At the design stage itself, prevent deadlocks. And the way to do that is that in general, you have circular waits when there is too much of symmetry in the system. So we will break the symmetry, as we shall see just now, that if you break the symmetry, typically circular wait does not happen. Right? So we'll immediately see an example. So consider the dining philosopher's problem, a very classical problem, where philosophers are sitting like this, and there are forks on the table. So forks, chopsticks, doesn't matter. So to eat, a philosopher has to pick up both the forks. So with one fork, he can't eat, right? So they're philosophers, right? So they have to eat with both the forks. It is possible that there is a deadlock situation. How? Why? You just, everybody picks up the right fork. That's it. And then the left side is empty. If you say that you drop it, everybody drops it. And as I said, in these cases, you don't rely on a global time base. It's more of an event-based thing, dependence-based thing. So if you drop it, everybody can drop it. Then let's say you say everybody pick left, they will pick up their left. So there has to be some way of breaking the deadlock, which means that one of these 4 conditions has to go. Hold and wait can be that either grab both or no preemption and mutual exclusion are not. Well, preemption basically means that you force someone to keep the fork down. Mutual exclusion, well, that doesn't make sense here. That almost never makes sense, violating it. And circular wait means you design the protocol in such a way that a circular wait is not possible. It's not possible by design. So in this case, what do you think should be done? There is a formal proof that symmetry breaking algorithms, which would basically in this case imply that n-1 philosophers pick their right fork first, but the nth philosopher picks the left fork. These strategies will not lead to a circular wait. So you can look at the book. So the formal proof is there, and the formal proof is not very hard, right? So you can prove by contradiction, assume there is a deadlock. If there is a deadlock, then all or whatever, these many processes would be involved. And then you can do a proof by contradiction that what would happen, so you would want to focus on the interaction of the nth and basically the nth, the n-1th, and let's say the first, right? What is happening in this region? If you focus on this region, you clearly get a contradiction that a deadlock is not possible because at least one of them would have both the forks. So then you can prove by contradiction that any such symmetry breaking algorithm, something of this nature, will not lead to a deadlock. So something similar can be done in the design of computer algorithms for preventing deadlocks. Does that make sense? Right? So this, in this case, what you are doing is that in a certain sense, you are stopping any sort of a circular thing from happening because circular dependencies would imply a certain degree of symmetry. And that symmetry is being broken. All right? So a deadlock situation is where all the threads, or a subset of them, and where the other subset are perhaps not interested, but let's say all, are kind of waiting on each other, right? So they are not making any progress in the sense, yes, they may be continuously looping to check if a lock has become 0 or not, but that is not really useful work. So this continuously looping is known as busy waiting or spin lock, or it's called a spin lock, where the idea is that you continuously loop and check, is it 0, is it 0, is it 0. This does take some, it does account for CPU time, it accounts for CPU energy, but you are not doing any useful work, nothing at all. So deadlocks, as I said, this continuous looping is the only thing you are doing, and that is not really helping. Then there is something called starvation. Starvation in the case of dining philosophers would mean that fine, you have a deadlock avoidance algorithm, all right. But it's possible that one of those philosophers is still not getting both of his forks. All right. So then, tries. For an indefinite period or infinite period, the philosopher is not getting both of his forks. In this situation is known as starvation. Right? So starvation means it's not fair. So starvation freedom implies deadlock freedom. Starvation freedom would mean what? That every philosopher is getting the forks in a finite amount of time. Finite or bounded, depends on the model, but at least is not waiting indefinitely. So then can you ever have a deadlock in such kind of a world? You can't, right? That is because a deadlock is denying you resources indefinitely. But if you have starvation freedom, then it automatically implies that you have deadlock freedom. But if you have deadlock freedom, it doesn't mean that you are fair. So deadlock freedom does not imply that you have starvation freedom. So go back to my crows and birds example, right? So it's kind of a one-way implication that if I'm not starving, there are no deadlocks. But no deadlocks does not guarantee fairness. The other is a live lock. So we will see examples of this, not super relevant here. Threads keep executing instructions, but nothing useful gets done. See, if let's say in a deadlock situation, if I consider executing instructions as a basic step, not entering the critical section a basic step, but just executing instructions, then they are executing instructions. They're continuously testing the value of the lock variable. So that is a live lock. If I look at this situation in this manner, because I'm continuously doing something yet doing nothing, I'm just going round and round in circles. So doing something yet doing nothing is a live lock, right? So live lock, we will see more examples of it later. This example is sort of contrived, but you get the broad idea of what is deadlocks, deadlock freedom, starvation freedom, which implies complete fairness, which also implies lack of deadlocks. But lack of deadlocks does not imply starvation freedom. So given that this part is clear, we will move on to some examples. Okay, let us now look at some examples. So what we'll be looking at is pthread code, and pthreads are the most common threading library on Linux, and they are natively supported by the kernel. So basically, the library uses kernel-specific, thread-specific function calls and system calls, and hence I'm saying that there is some native support. So what you need to do is you need to hash include pthread.h. That is all that you need to do. So here what we will do is that we'll create a function. We'll run that function concurrently or in parallel. So what we will do here is that we will actually start 2 threads, and we will thus have a for loop for 2 iterations. So the first thing that we will do is that we will send an argument along with the thread. So for that, we will initialize a pointer. And as you can see, we are initializing a pointer here, an int star pointer. And we're setting the value of the pointer to the iteration number. So which means that one value will be 0, the other value will be 1. So the most important function call over here is pthread create. All right, that is what we are doing. And so here, of course, I have an ID of thread. So I'm not, okay, so it's defined over here. So this is a global array where pthread t is nothing but a pthread type. I'm pointing to that. So since I'm creating 2 threads, I have an array comprising 2 pthreads. And what I'm doing is that I'm providing a pointer to the ith thread. So I'm providing a pointer to it such that the pthread create function can create a pthread and populate the pointer. All right. Then what I do is I provide a function pointer. So the function pointer's job, so pthreads take sort of a standardized function. So the function that they take, which they execute, is void star func void star, which means you can pass as an argument a pointer to anything, and it will return a pointer to anything, which basically means this is as flexible as things can get, where anything you want, you put it in a structure, you send a pointer to it, and anything it wants to return, it will put it in a structure and send a pointer to it back. All right, so this is a generic thing. So what you actually pass to the pthread create function is basically a function pointer and an argument. So in this case, the argument has to be sent as void star. So I'm sending an int star, which will internally be typecasted into a void star, because anything can be typecasted into a void star. And then the function, so I'm just initializing a thread, all right? And then, of course, the thread will run whenever the scheduler wants it to run, and it is going to run and it is going to return. All right. Then if there is an error, in the sense that you expect this error code to be 0, but if the error code is non-zero, then you can see that an error was encountered in creating pthreads. It was not able to progress. So now let us look at this function whose pointer you are passing. So this function is taking a pointer as an argument, And in this case, the pointer is this ptr, whose value is the iteration number. So what we do inside the function is we have an int star ptr, which is which you are typecasting into int star argument. All right. So you're essentially typecasting it back, and you are saying that I am thread %d. So %d is the contents of the pointer. So it is either 0 or it is 1. All right. So then you are creating two such threads. So you are creating two such threads and they are either 0 or 1. So what is essentially happening is that you are either printing 0 on the console or you are printing 1 on the console. Then once the main thread, so basically I have a main thread like this. It has created one child thread and it has created one more child thread. So it waits for these child threads to actually finish. So you can call the pthread join call, which waits for tid 0 to finish and it waits for tid 1 to finish. All right. So far so good. And it waits for both of them to finish. And once they finish, essentially they finish like that and you go forward. All right. So this is how you create threads where you are assigning a thread a function pointer. But of course, this is kind of a special way of creating a thread. And the function, mind you, is written in such a way that it can run even without the thread. It can run, the main function can call it, a thread can call it. The function is generic. But clearly, when you are calling it in a thread, you have to play the same trick, which is tweak the return value, such that when the function returns, the function will return to a specific point within the thread. All right, so this can be done because when it is being invoked, you are tweaking the return value. So it will return to that point and the thread will be torn down. Okay, so the entire thread will be torn down after that. So that is the significance of this function. All right, so far so good. So we can look at a more complicated version of this example, and so we can see if this file opens here. We'll do that. So we'll now look at a slightly different version of the same example where you actually return a result. In the earlier case, we were not doing that. So we are doing the same thing over here, which is that we are creating a pointer to the argument. We are creating a pthread create call. We are creating a pthread thread. And we are doing the same thing, pass an argument to the thread, the function and its argument. All right. But what is actually different in this case is the function. We are printing, that part is correct. But what we are doing is that we are allocating a return value. So what you need to understand is never send pointers to local variables. Because if you send pointers to local variables, they are defined on the stack, right? So once you exit the function, your stack folds up. The moment your stack folds up, then the pointer to the local variable does not make any sense. So if you want to send a pointer, that pointer has to be defined on the heap, right? So that is why you need to do a malloc and define the pointer on the heap, right? So never ever make the mistake of sending a pointer to a local variable. It can be done if it is one of the functions you are calling and a callee is using it. Again, that's not desirable behavior, but that's perhaps the only point of time in which it is, even remotely acceptable. Otherwise, never send a pointer to a local variable. So what you do is that you create a new return value. You malloc 1. And then whatever value was there in the pointer, you multiply it with 2, which means you're multiplying the thread ID by 2. And then what you do is you set the return value as this, and then sorry, there is one part that is missing, which is that you return the return value, right? So the return value is something that you return, because this is a void star, right? So something has to be returned. So then what you do is that when you want to join, what you basically do is that you declare an int star result. It's a pointer, and you send the address of that pointer to actually the pthread join call. So whatever is the return value that it is getting from the function, it will put it over here and it will return. So in a certain sense, your pointer will start pointing to the return value, will start pointing to retval. So retval is a pointer, but whatever retval points to, this will also start pointing to the same thing. So of course, this is something that you may not have seen earlier, which is a void star star, is essentially a pointer to a pointer. So what you are basically doing here is declaring a pointer here. But this pointer in this case is a value, and the value is the address. So when you send the address of result, essentially someone can populate that with an address. In this case, the address corresponds to the address that the thread function generated. All right, it's the same address. So what then you do is that result comes back populated from the join call, and then all that we do is we print star result. So star result will dereference the pointer and actually print the value, which is 2 times the thread ID, right? So what you need to understand over here in a certain sense is that in this function over here, there is a need to actually look at this pointer and pointer to pointer business. So you can design a small diagram. So we can also draw it, where the idea is that the return value over here, the return value cannot be sent, because as you can see, the data type here of the return value is actually a pointer. So you define a pointer and you send that, right? Fair enough. But the way that your pthread join call works, pthread join call expects a pointer to a pointer, such that the void star pointer that you got, that can be populated and sent back. So you kindly meditate on this example, right? And maybe I'll draw a small diagram for you. It will kind of make things slightly clearer. So let me do that. So let us now see what is happening, and let's draw a little diagram. It will make things easy to understand. So we have a return value, which is a pointer, which is in the func call. So let us have the func call. We have return value, right? Retval, which is clearly a pointer that is pointing to somewhere in memory. And this place is containing the value that we want. All right. So what this function call is returning is nothing but retval. So let's say this address is 100 and the value here is 4. So what it is returning is this address 100. It's returning an address. All right. It is not returning 4. It is returning address 100. If I go to memory with address 100, I'll get the value 4. But it is important to understand that what is being returned is 100, not 4. Right? Is this part clear? The reason that this part should be clear is because I have a void star over here. Void star means it points to anything, right? Which means it's an address, and that's exactly what I'm returning, which is I'm returning 100. But as I have said, these functions, they return to a custom area within the kernel. Not within the kernel, but within the pthread library code. So the pthread library code, so now if I see my main function, so something interesting is happening down there. I have result and result is a pointer. All right. Currently, it has no value. Right. So result currently does not have any value. But the result variable is stored somewhere, right? So wherever it is stored, so maybe result is stored over here. Correct? So this point has an address. Let's say the address here is 20. So if I just look at the code, you will see that I have declared an int star result. And so this is a pointer, it stores an address. But the thing is, this is on the stack. And in this case, I'm passing an address on the stack because it is again returning back there. Its life is limited to the address of the function. So this is, I said, one of those cases in which this is acceptable. So let us assume that the result is stored in address number 20. So when I send AND of result, I am not sending what result contains. I am sending where result is contained. Right? That is important. I am not sending the contents of result. I am sending the address of result. So the moment I do pthread join, what I am sending is I am sending 20. Why? All right. Now what is happening is something very interesting is happening. Inside pthread join, it is only seeing address number 20. What does pthread join have? It has address number 100. So what pthread join does is that it writes 100 over here. Is that clear? It just writes 100 over here and it returns. That is exactly what is happening. I send the address of result and result, which is 20. It writes the address internally over here of 100. Okay. Now what I do is when I do printf, what am I doing? Star of result. In this case, what is the value of result? The value of result is 100. What is the value of star of result? It is the dereferenced value. So I go to address 100 and I see that 4 is written. So ultimately this becomes 4. Is this clear? So using this mechanism, I am able to print and I do it for the second thread. So what is clear is, so let us understand the significance of why void star and star star and these were used. So these are complex concepts, but as I said, C and C++ programming is required when you build systems. And also if you think about it, any construct you are using in Python or JavaScript, ultimately under the hood it is using this only. It is not using anything else. It is using this only. All right. Because it is using this, it is working, and that too working efficiently. So in this case, I want pthread to execute any function. Any function means it needs to take any argument. How do I make it take any argument? A standard way is I put all the arguments in a structure. I pass a pointer to it. Correct? Then it will become any argument. And that is I don't know what kind of a structure it is. I say it is void star, which means it's just an address. Right? The function is supposed to know what it points to. Similarly, when I return, I want to return anything. So it can be int, float, 5 ints and 9 floats. Again, I put it in a structure. In this case, this can't be a pointer to a variable on a stack because it is being accessed after the function is finishing. Right? So this is not allowed. I do a malloc, take space on the heap, put in everything that I want to put in, and I send a pointer back. All right. So that is why the argument has to be void star and the return value also has to be void star. But the fun doesn't end here. Now, if let's say the parent thread would like to read the value. If it would like to read the value, there can be two options, right? Let us evaluate both the options, because here I'm assuming that we are kind of designing the API here. So if I have pthread join, of course I'm giving the thread ID and other stuff. The first option is that I return a void star, which is the result. Okay, that is the first option. But this is not a good option, because number one, it is violating our template, because we want the first option to actually be whether pthread join worked correctly or not in the first place, right? So we want it to actually be an error code. So that is how we have defined all our system calls, all our library calls, everything. The way we have defined is that this is an error code, where if it is 0, it means that all well. If it is non-zero, it means that there was some problem. All right. So if this becomes the error code, how do I return a value? Right, I'm already returning the error code, so I have no option of returning. But you want me to return a void star, and I clearly cannot return two things. So what is the only option that is left with me? The only option that is left with me is that I send an argument which is a void star star. Void star star is basically a pointer to a pointer, where what I do is that, so it's basically a pointer of a pointer, where the argument is a pointer. So in my base code, I'm sending I have a pointer, and then I send the address of that pointer, such that all that it does is, so let's say this is void star star p. So you will say p is equal to result, or whatever, right, that you got from your function. Or you can, if I want to do it simply, then pthread join would basically set this as the return value of the function, right? So this is tantamount to, so I get a return value which is a pointer, and I set star p as return value. This is tantamount to actually returning, because you sent me a pointer, I'm populating it and giving it to you. So this is tantamount to returning. Of course, this has to be done this way. It can't be done any other way, because my return value from pthread join will be an integer. So the only way is, in the argument you give me a pointer, I'll fill it up and give it to you. Now the question is, what is the data value of that pointer? It's a void star. So the argument has to be a void star star. There is no other choice, which is why we have designed the code in this manner. And you will see this pattern all over system code, that you have pointers to pointers, so on and so forth. So let us now extend this example to actually looking at a function which increments your global count variable. So in this case, what we do is that we initialize a lock. We need a lock. There are multiple threads, we have to have a lock. A lock is called a mutex. Mutex stands for mutual exclusion. A lock is called a mutex. So we init a mutex. So what you define is, you declare the lock, you send a pointer to the lock for initializing it, and some additional arguments. We are not interested in that. And you initialize it. Subsequently, when you want to lock, all that you do is you call pthread mutex lock with a pointer to the lock. So it will then, kind of busy loop, wait for the thread to acquire the lock. And the moment it returns, you know that it is returning with the lock acquired. Then you increment the counter, and then you unlock. As simple as that. That's all that you need to do to acquire a lock call and an unlock call. If you want, you can put it in a macro, it will become even easier. But this is broadly speaking what is happening, that every lock has to be initialized first, which sets its starting value. and then you lock and you unlock. Do it hundreds of times, no issue. There is an option where I can avoid locks by using built-in hardware support for atomic update. What did we say atomic was? Atomic means that an operation appears to execute instantaneously, right? Appears. The key word here is appears. Appears to execute instantaneously, right? So, so we have a full course dedicated to getting deeper into the meaning of appears. All right. So, as far as we are concerned, it basically means that nobody sees an intermediate state. Either it is done or it is not done. So, in this case, you can use std atomic.h and define count to be an atomic integer. Then what you can do is you can use the atomic fetch add function, which wraps a machine instruction which atomically increments a value. Fetch means fetch its current value, add 1 and return. Right? So these 3 steps happen in one go. There is a hardware instruction in Intel that does that. So we will see that every architecture has to have this. So in this case, all that you do is pass an address to count and say that you do count is equal to count plus 1 atomically and you return. So in this case, you do not have to use locks. This is known as a non-blocking algorithm because there are no locks, there is no waiting. This is also known as a lock-free program. Does that make sense? Right? So this is a lock-free program. The reason is you are not using locks, and if in this case, of course, what we want to do is simple. Just increment. You can use the hardware instruction and the software wrapper on top of it. So then we will see. So as I said, we have a full course dedicated to appears. So appears is such a strong concept in concurrent systems theory that we have a full course dedicated. Even there also we need to take extra lectures, right? So I mean, our standard 42 lectures is not enough. We typically squeeze in a few more. So I want to tell you in a nutshell that count is equal to count plus 1 is essentially a weak operation, right? Whatever that means. It's a weak operation in the sense you can do this for count is equal to count plus 1, but let's say you can't use it to implement something like a stack or something with, 3 parallel threads, right? That is going to be much harder. Well, it's actually impossible, and there's a proof for it, but let's not go there. So things get very complicated, but let's say there's a weak operation. That is why all hardware have to support a strong operation. The strong operation is compare and exchange. It's also called compare and swap, right? So we will see what it is in a second. So if you use the compare and swap primitive, then you do the same atomic int count is 0. And you define, so in this case, just to make life easy, I also didn't want to type so much. So I defined a shortcut for atomic compare exchange strong. There's a compare exchange weak also, but let's not go there. But all of these things are, if someone wants to be an effective C++ programmer, understanding weak, strong, etc. is very important. But as I said, we can't teach so many things in one course. So hash defined cas is just a shortcut for this long string. So here I want to fetch an increment. I want to fetch something, the current value, add something, write it back, all of them happening in one go instantaneously. That is the way it should appear, right? So what I do is I define 2 temporaries, old val and new val. The first thing is I fetch its current value, which is old val. This I use the atomic load command. And again, I can't tell you much why it is used, right? We will discuss a little bit in the theory of non-blocking algorithms next lecture. But let's say that atomic load command is required. Then I want to replace this with old val plus 1. So I compute new val is old val plus 1. Then I print the values. That's all right. Then the secret sauce lies here in cas. So I provide it an address to the, sorry, this should be count, right? So this should be count. So I provide it an address of the count variable. And then what I do is I give an address of the old value and the value of the new value. So why one is address, one is value, we can discuss that later. But the key thing is it will compare the current value of count with the old value. Is it still what you have read or has it been updated in the middle? Because we are assuming that between two instructions, the delay can be indefinite, right? So first is you check if it is still the same or not. If it is still the same, then you replace the old value with the new value, else you return false, which means it will try again. If it's true, you get out, else you return false and it will try again. So this is compare and swap or compare and exchange. And this is an atomic instruction which this atomic function wraps, right? Atomic compare exchange strong function wraps. My claim is that this is a strong operation in hardware, whatever that means for the time being. But this any hardware has to implement. There is no other escape. And this may sound to be slightly more complicated than the previous one, but the previous one is fine. Previous one just for incrementing is fine. But with this, you can implement any concurrent algorithm regardless of its complexity, like a concurrent queue, stack, linked list, you name it, right? That can be done. Fine. So this is atomic compare and swap. So the output, as you can see, is that the old value is 0, it's 1. So it's the same printf. So there can be many failed attempts. So it is possible that if there are many threads, then and they are doing this compare and swap, many of them are failing. They are failing because someone is being successful. So the system as a whole is making progress because one thread is successful, but such approaches are prone to starvation. But the previous approach, where the hardware was guaranteeing fairness, was not prone to starvation. This was not prone to starvation. So if it's not prone to starvation, then it is also said to be weight-free. Right? A weight-free program is lock-free, but a lock-free program is not necessarily weight-free. So when there is no starvation, it is weight-free, but this is not weight-free because there can be starvation. So our current lecture ends here. So what we will do in the next class is look at the broad theory of these non-blocking algorithms and of the synchronization and concurrency area in general. The reason we are doing this is to create a strong background or a strong base for creating concurrent data structures which we'll ultimately use in scheduling tasks and scheduling resources.